May I introduce the next speaker, Mahdi? Mahdi, I think you are co-host. Jose, may I ask if you can add Mahdi Momeni as the co-host? Yeah, thank you very much.
Okay.
Yes.
Okay.
Yeah. So hi Mahdi.
Hi. Hello.
Hey.
Yes.
Yeah, thank you very much. Thank you very much for your paper. So this is the industry paper that you're presenting about rebar installation, which is automated fabrication of the rebar cages.
Yes.
Yes.
Just let me do the settings, and then I hope you can see.
Yes. Yeah, perfect. So the floor is yours.
Okay, thank you. Hello, everybody. My name is Mahdi Momeni, and I'm a PhD candidate at Mälardalen University in Sweden. I'm working on automation fabrication of rebar cages using 3 industrial robots hanged on a gantry. Actually, Skanska and ABB are also part of this project. So in this presentation, I'm going to discuss and present part of our achievements on bar installation order for the automatic fabrication of rebar cages. So we have already implemented and demonstrated the fabrication using this system, gantry robot, as we call it, system, but there were some challenges that we are still working on those challenges. So yeah, the presentation outline. I'm going to discuss a little bit about the introduction, why we are working on this, and like problem statement, methodology, and results. So despite the significant development of automation, actually technologies and their application in manufacturing industry, construction industry has not really gained that much from it. So, for example, rebar cages are still being fabricated manually, either on site or off site. Actually, yes. One reason is that there are among so many benefits that automatic fabrication can have. Actually, it helps to save construction time. Yet, this is not a trivial task, despite the advanced automation and robotic technologies and systems available like commercially. There are so many challenges that they have to be tackled before this idea can come to life. One major challenge in automatic fabrication is how and in what order the rebars should be placed one after another, or in a sequence to be able to fabricate the entire cage. So this is like a big challenge. We call this actually sequence an installation order. And please note that not all sequences are valid, because in theory, the number of I will explain this in future also in the next slides. In theory, the number of solutions are like equal to the factorial of the number of actually rebars available in a cage. So not all of them are actually valid. A valid sequence should allow a collision-free path. Yes, for the problem statement, we can formulate the installation order problem as like, given the digital twin of a rebar cage, we need to find a feasible order which allows to fabricate the entire cage. Like we discussed, finding such an order is not trivial. It's like we have like we can have like hundreds of rebars in one cage or in different cages. So this is not like finding this solution or this sequence is not really easy task. It's really challenging. Actually, for now, we are not interested in an optimal solution. We just want a solution. For us, that's enough at this stage. Any solution actually satisfying the following constraints and assumptions would be okay for us at this stage. The constraints are the rebars should be installed following a vertical movement. We have this constraint because we already developed a motion planning algorithm. We already presented in another journal paper. So in order to comply with that system, this is the reason we have this assumption or constraint. So the rebars should be installed following a vertical movement, and the rebars also should stay connected, meaning that we are not no rebar is allowed to float on air. This actually I will discuss this a little bit more. In order for a cage to be built properly and be usable, if you can call it, the cage should be stable. But stability is like a very challenging actually definition, and we have a lot of different parameters. So for now, we just a relaxation of that stability. We just define the rebars to be connected, but connection is not enough. You can refer to our future papers or even the paper that we already published to get better idea what we mean here. We don't have time to discuss all these things, unfortunately, now. The time is limited. So for now, we assume that the rebars are connected. And we assume that the rebars are stiff, meaning that we don't have any deflection or deformation or actually deviation in the rebars. Yes. So these are the assumptions that we have. So for the methodology, in order to find the solution, we would like to use some heuristics to guide a depth first search in a way to increase the likelihood of finding a feasible actually installation. During our observation, we observed that rebars with horizontal legs are acting as an obstacle, like to install the next bar. So we can use actually this observation to formulate our methods. So the heuristics that we are actually using, or the method we are working on, we find a solution actually based on all these things. So we have to place a system coordinate frame anywhere on the floor, and then we assign a height coordinate to each rebar, or the Z coordinate actually, with respect to the system coordinate frame we already defined. And then the cage is considered as different layers. Each layer corresponds to the Z coordinate of the rebars. And we initialize the search algorithm with a list of rebars where the order is from lower to higher. This means that the cage, the entire cage, will be fabricated from bottom to top, layer by layer. So, oops, yes. So we actually case studied this method. We tried to simplify a cage that which has already been designed for a bridge structure in Stockholm. And so the number of rebars that we actually tested the algorithm are 44 actually, and we have like 3 different types of bar. I mean, in this specific simplified cage, we have in Swedish standard, we call them A bar, B bar, and C bars. So let me see if I can show the simulation here. I hope you can see the screen also. So this is just a simulation for the demonstration. We will present it like in future works. So now you can see that the rebars are placed one by one, layer by layer. So we have this like Z coordinates for each layer they are being placed. Yeah. We have different layers. So these are these bars with horizontal legs that they're acting like as an obstacle. So as you can see, they are being installed after these rebars are actually installed. Then we install the other A bars or these straight bars, and the B bars to finalize to fabricate the entire actually cage. So yes. Oops. Oh, sorry. Yes. So as you can see, for example, we have like in this simplified cage, we have like 8 different layers with different colors. As we briefly discussed, reverse connection is just a relaxation of stability requirement. We will address this stability in our future works, like in more details. And in this version of the installation order, we have not taken into account the gripping point and the tying point of the rebars, and neither the reachability of the tying tools, because we developed a prototype in order to tie the rebars together. In Swedish standard, we are not allowed to weld the rebars. I mean, we can weld the rebars, but not all the time because of the fatigue things that we have. So we have to tie them together. So we developed a prototype. There are some commercially available tying tools as well, but they were not good enough for us. So we had to develop our own tying tool. So reachability is not actually taken into account in this installation order. And these are just going to be addressed in our future works, these things. Thank you so much. And if you have any question, I'm available, please.
Thank you very much, Madi. So is there any question from the audience online and on site?
From the audience on site, there are no questions.
Okay. So maybe I also want to ask one question. So Madi, you mentioned at the beginning that ABB is also participating in this research. So did ABB build this gantry robot system with the picture that you show in the paper?
Yes, they help us fabricate, actually build this cage. Yes, so we are borrowing ABB robots from there and their drivers for the motors. I mean, you can see, I think, I'm not sure if it is visible in the background or not. So this is our lab with the gantry and robots, the background image. So we borrowed the robots from 3 ABB robots from ABB, and they helped us build the gantry, yes.
And they help with the technology as well?
Well, with the technology, if that means commercially available technologies, yes, we are borrowing from them. And but with the algorithm, with the planning, motion planning, path planning, and everything, all the cutting edge research, we are actually working. Skanska is also helping us with the design cage, to design the cages and all those things with the construction, because I'm not a construction engineer, I'm like a robotic engineer. So with the construction, Skanska is helping us. I'm not sure if I answered your question or if that was your question.
Yes, thank you very much, Madi.
Yes.
So I have a question from Giovanni.
Yes.
So so he's asking about did Madi and your team manage to develop the tying and grabbing points?
Yes.
With the ABB robots, yeah.
Yes, so we developed a prototype. I mean, this prototype is not finalized yet. So one of our partners, Husqvarna, they are also helping us to develop this prototype for the tying actually tool in order to tie the rebars together. Yes. We are also doing that. It's not finalized, it's still a prototype, but yes, we are working on that too.
Thank you very much, Madi and Giovanni.
Yes.
Thank you very much, Madi, once again for your presentation. So in this case, I would like